In this chapter, we're going to distinguish between single, double, and triple bonds, and then also recognize these in Lewis structures. So we've already seen single bonds in the previous video. So a single bond is going to be just a single line, which represents 2 electrons. We can then have a double bond, which is going to be 2 lines, which represents 4 shared electrons between 2 atoms. And then lastly, we can have a triple bond, which is 3 lines, which is going to be 6 shared electrons between 2 atoms. So this example wants us to figure out how many single, double, and or triple bonds we have in this Lewis structure example. So let's look at each bond. Again, any line is what we're looking for. So here's a single, here's another single, there's the third, fourth, and fifth. So there's 5 single bonds in the structure. Here we have 2 lines between 2 atoms, so that's 1 double bond. And we do not have any triple bonds because there's no 3 lines between 2 atoms anywhere. Next question is, how many total bonding electrons are there? So we have a total of 6 bonds. So we've got the 5 single. So 5 single bonds is going to be 5 times 2 electrons. Plus we have 1 double bond, which is 1 times 4 electrons. So that's going to be a total of 14 electrons in this structure. And then how many lone pairs are there? Remember, lone pairs are the 2 dots that are not between atoms, and these will always be drawn as dots, so it makes it a little bit easier to distinguish when we're doing lines for bonds and dots for the lone pairs. So there's 1 lone pair, and here's a second lone pair. So we have 2 lone pairs in this structure. In this video, we're going to talk about the octet rule again and how we can determine what types of bonds versus lone pairs atoms are going to prefer to form. And we're going to focus in on oxygen, nitrogen, and carbon. So oxygen is in group 6. And remember, our group numbers tell us how many valence electrons it has. So oxygen, we're going to go back to our Lewis symbols for atoms. So there's 4, 5, 6 electrons. So it already has 2 lone pairs. However, it also has 2 electrons that are by themselves, and it's missing 2 electrons to get a full octet. So what oxygen prefers to do is it's going to go and find 2 electrons from other atoms, whether it's sharing as a double bond or 2 single bonds, and that will complete its octet. So what oxygen prefers to do is have those 2 lone pairs and form 2 bonds. Again, whether it's 2 single or 1 double, either way that will fill oxygen's octet. And what it's bonded to doesn't matter. Okay, it can be any element. But that's the normal bonding pattern for oxygen. If we look at nitrogen, nitrogen is in group 5. So it has 5 valence electrons. So its Lewis symbol will look like this. It has 1 lone pair and then 3 single electrons. So it's going to need to add 3 more electrons to fill its octet. So each of these single electrons will go and find another element to share with. So by adding those 3 electrons, we now have 8 around the nitrogen. So what nitrogen's normal bonding pattern looks like is 1 lone pair and 3 bonds. So there's more combinations here. We could have 3 single, like you see. We could have a double and a single, or we could have a triple bond. So nitrogen could do any of those. But again, it's 1 lone pair and 3 total bonds. Then we have carbon. Carbon is in group 4, which means 4 valence electrons. So carbon typically does not want to have any lone pairs. It's going to need to find 4 more elements to share, or 4 more electrons to share to make its full octet. So that means it is going to want to make 4 bonds. So if we look at the options, we can have 4 single bonds. We could have a double and 2 single. We could have 2 double, or we could have a triple and a single. So these are your common bonding patterns for oxygen, nitrogen, and carbon. And we say common because it's not a hard, fast rule that all structures have to have these patterns. We'll see in this chapter some examples where they don't. In later chapters, when we're talking about hydrocarbons and doing organic chemistry, we will follow these patterns, which will make drawing Lewis structures a lot easier. So we're going to take what we just learned about oxygen, nitrogen, and carbon and see if we can predict what will then be the patterns for sulfur, phosphorus, and silicon. So remember, if valence electron count is based on group number, valence electron count then determines the number of electrons we need to add to get to a full octet, which then determines the lone pairs versus bonds that we just looked at. Anything that's in the same group is going to have the same patterns. So oxygen and sulfur are in the same group, group 6. So we said oxygen wants 2 lone pairs and 2 bonds. So that means sulfur is also going to want 2 lone pairs and 2 bonds for the same reasons. Nitrogen and phosphorus are in the same group. Nitrogen, we said, wants 1 lone pair and 3 bonds. So phosphorus is going to prefer 1 lone pair and 3 bonds. And then silicon and carbon are in the same group. Carbon wanted the 4 bonds. Silicon will also want 4 bonds.